So today we're going to see compact operators and some properties, theorems and corollaries of compact operators. So I'm going to start with a lemma or a corollary. So let X be a norm space, Y be a Banach space, and Tn from X to Y, that is the set of bounded linear operators from X to Y, be a convergent sequence of operators such that the dimension of image of Tn is less than infinity. So X is a norm space, Y a Banach space, and Tn is a convergent sequence of bounded linear operators such that the dimension of image of Tn is less than infinity. Then we say that its limit T is compact. So what I can say is Tn minus T is equals to 0, limit n tending to infinity. This is what it means. So Tn be a convergent sequence of operators, and this limit is compact. And next we see a lemma. The lemma says that let X be a norm space, Y be a Hilbert space, and T from X to Y be a compact linear operator. Now, there exists a sequence Tn in Lxy with dimension of image of Tn less than infinity and limit n tending to infinity T minus Tn equals to 0, which means that T is the limit of Tn. So what it means is, earlier we said that X was a norm space, Y was a Banach space, and we said that if we have a convergent sequence of operators, of bounded linear operators, such that the dimension of image of Tn is less than infinity, then its limit T is compact. And now what we are saying is that all compact operators are precisely the limit of sequence of operators with finite dimensional ranks on Hilbert spaces. So now what we essentially did is that we proved the converse of the theorem that we saw above. And the summary can be said that if you have a finite rank, then the limit must be compact. So I'll repeat it again. If you have a sequence of operators with finite rank, then the limit must be compact. And now we see that this was proof of Banach spaces, that if Tn was a convergent sequence and dimension of image of Tn is less than infinity and T is the limit of the sequence, then T is compact. But however, for Hilbert spaces, it changes to an if and only if condition. That is, all compact operators are the limit of sequence of operators with finite dimensional rank. So that's one point. And the next thing that I would like to show is, so let us discuss pointwise continuity at X. By pointwise continuity at X, I mean for every epsilon greater than 0, there exists a delta greater than 0 such that norm of x minus y less than delta implies that the norm of f of x minus f of y is less than epsilon for all y belonging to x. So this is what I mean by pointwise continuity. Now I extend this notion of continuity. Now I say that this continuity does not depend on x at all. It is independent of x. That's why if I look at, say, like this line, like a straight line, and my artistic abilities are limited, so I'm not able to draw it straight enough. So here I had continuity, the pointwise continuity. So this continuity, this distance between f of x and f of y was depending on where I am. But now here, for every change in epsilon, or for every change in epsilon, the change in delta also remains to be the same. So now I say that by definition wise, uniform continuity means that for every epsilon greater than 0, there exists a delta greater than 0 such that the norm of x minus y is less than delta implies that the norm of f of x minus f of y is less than epsilon for all xy belonging to capital X. Now I further extend this notion. I extend this notion to a subset f of continuous functions being equicontinuous if for every epsilon greater than 0 there exists a delta greater than 0 such that f of x minus y is less than epsilon with norm of x minus y less than delta for all f belonging to S. So this time this continuity is over the subset of functions, of continuous functions, see omega, where omega is a norm space. It's some kind of like super continuity that I am continuous over the set of all such functions, or the set of all continuous functions defined over omega. Now once we have understood what equicontinuous means, we would summarize it, we would say that it's not just uniform over the points, but over the functions as well, this continuity. Now we move to the Ascala-Ascoli theorem. Let omega be a compact subset of a Banach space. Now suppose that the subset S of C of omega is bounded and equicontinuous. It follows that S is relatively compact. So what happens here is that now omega is also a compact subset of a Banach space, and the subset S, uh, which is in C omega, which is continuous functions defined on omega, is bounded. Now, what do we mean by a bounded subset of a Banach space? It just means that S is bounded subset of X. It means that there exists M greater than 0, such that the norm of X is less than or equal to M for every value of X belonging to S. This is what I mean by a bounded subset of a Banach space. Now, what I'm saying is that suppose that there is a subset S in C omega which is bounded as well as equicontinuous. So by equicontinuous, I mean this, that for every epsilon greater than 0, there exists delta such that this condition holds true for all f belonging to this S. Now, if this S satisfy all these properties, that it's bounded, it is equicontinuous, then I say that S is relatively compact. So yeah, to summarize it, a subset S of continuous functions on omega, if they are bounded and equicontinuous, then this subset S is relatively compact as a subset of C omega. So this is what we mean. And further we move on to an example which puts all these ideas. Now let K be an element in C01 square, which means that the set of continuous functions on 01 square. Now I define an operator T as follows. Now since K is uniformly continuous, how do I know that K is uniformly continuous? I just saw that it's continuous. How does the uniform continuity apply from here? Well, I can see that because continuous functions on compact sets are uniformly continuous. So this 0, 1 closed interval is a compact set, and thus K is also a uniformly continuous function. Now, since it's uniformly continuous for each epsilon greater than 0, there exists delta greater than 0 such that if K of x1 comma t1 minus K of x2 comma t2 whole norm is less than epsilon for all x1 t1 and x2 t2 belonging to 0 1 square, with this condition holding true. So it just means that the same definition of continuity that we saw above. Now I will use this here. I will use this here as follows. I would say that if I estimate this quantity here, I would see that tfx1 minus tfx2 whole norm, it's less than this. Now I just use the definition of t of f and I mod it up, and I would see that this can be estimated by epsilon, and the norm of f of t can be just be approximated by the supremum over all f. So next I see that this is less than epsilon times the infinity norm of f. So if I take f in a ball of radius 1 centered around 0 in this, in C01. So this F is in this ball. Now if I do so, then I see that TB10 is equicontinuous. How would I say that? But I would say that because when I look at this definition here, I see that if so I look at this definition, I see that this TF is an element in C01, because you see this F is in C01, and next what I see is that for all such F in a ball of radius 1 centered around 0 in C01, this quantity is less than epsilon. This norm of T of x1 minus T of x2 is less than epsilon, and it is independent of F. So I can say that all such T of F's are equicontinuous. So that's why I say that TB10 is equicontinuous, because for all functions in T of B10, this is less than epsilon with x1 minus x2 less than delta. This is just the definition of equicontinuity. And then I prove that T of f is also bounded. So by bounded, I just mean it is less than some quantity for all f belonging to the ball. Now I showed that this set TB10, which is a set in C01, it is equicontinuous and it is bounded. Therefore, by the Ascala-Scauli theorem, I can say that TB10 is relatively compact, and so T is compact. Now we prove the first result. We show that the annihilator of image T is same as the kernel of T star. Thing to remember here is that T is an operator from X to X, while T star is an operator from X star to X star. Now we see that the annihilator of image T is precisely the set of all f belonging to X star such that f of y equals to 0 for y belonging to the image of T. Now I see that f belongs to X star. These are precisely those f that belongs to X star, and I just write instead of y T of x for all x belong to capital X. That's why I get this, because y is image of T. And when I write the definition of kernel of T star, I define kernel of T star as all of those f in X star such that T star f equals to 0. But this just means that all of those f in X star such that T star f x equals to 0. And I know that it is the same when f of t is equal to T star f. That's the condition for the Banach adjoint, and thus I can say that the annihilator of image of T is equals to the kernel of T star.